Hello. This is a demonstration of some of the properties of the solver, the equation solver, in the SFC models Python package. I'm using as an example the external model, which I described in another video. A little bit of economic background. What's happening is in this model, it's similar to what was in Godley-Lavoie's model in their book Monetary Economics. It's a gold standard with a pegged exchange rate, and every accounting period, central banks intervene to balance out the net trade flows. So what you see here, this is the gold purchases, and this evolved over time. There's two countries, north and south. They have N, so that's noted by N. This is what the time series look like. If we look at the equation here, the gold purchases, we actually see it's defined as the gold purchases minus the net position in Forex in the north. It's a looping sort of recursive definition. And what this does, if we go to X, the net position, see the net position is equal to gold purchases, which is defined there, and then you have the goods supply from this. These are the imports and exports, and so these two terms, there's an exchange rate on one. It's in the local currency of the north, currency N. So this flow is denominated in the southern currency, so there's an exchange rate, there's a cross rate between them. And what this did is it nets out to zero. So the gold those two equations together ensure that this thing is also equal to zero. It's if you're solving this by hand, you just say, oh, that's zero, and you can just get rid of it. We don't have that option. We have to solve all these equations properly, and so we have to actually determine that, yeah, this thing is actually equal to zero, because various things could happen that drive you away from zero. And but although this seems clean, what's happening on the solver is interesting. This here I set in the model to look at, for one step, how do the variables converge. So this is just one time period. So this is the iterations. Actually, we'll go back. There are more iterations. And so it took just over 80 iterations to converge. Okay, it's actually, yeah, it's 5. So this is a period 5. So we're solving for one time period, and we're trying to calculate what is the value. And the time period doesn't change, because this is the iterations for finding a solution during time period 5. And what we see here is that the variables swing around, and this is the net position in the north, and we're seeing it swing back and forth. It's oscillating, converges to zero. This is the absolute change. It's how far you are away from convert. During each step, what's the sum of the absolute value of all the changes? And we see it's actually exploding, getting fairly big. It's high, and then around here it suddenly comes down. What's actually happened is that this solver, it's based on I saw they use it in MATLAB code, but this is a classic fixed point theorem convergence, that if you say x equals f of x, you're just saying the new guess equals x is f of the previous guess, and you just keep iterating. But what that does with, see here, the lags in the system cause this thing to oscillate, and then until period 10 they're just bouncing back and forth, and then suddenly it's coming in. What's actually happened is at period 10, which is currently a hard-coded parameter, what the algorithm does, this is an innovation I added. I have no idea Whether this is a standard technique or not, I didn't bother looking at the literature. I'm not an academic, that's not my problem. And what it did, after period 10, I clamped down on the size of the moves. Instead of saying the new guess is equal to the calculated value, I say we're not going to go all the way to f of x. We're going to go to the midway from the old to the new. And what happens is that variables can't move as quickly. And so it forces them to have smaller steps. And then what happens is on these iterations will actually converge. And so you see, and then comes down, and again they're smaller and smaller, and then until it hits my tolerance. I mean, they're not, it's still not exactly equal to x equals f of x, but it's close enough for it's within the tolerance. And so this is the sort of problems we see. We could have redefined the equations, to eliminate this oscillation. We could have applied algebra, and rather than recursively define the gold purchases, we could say the gold purchases are going to be equal to all the other terms that go into the x-test. So it cancels them out, and so that it's zero. It wouldn't oscillate, but then that's a problem for the algorithm. Because, see, this is a nice, simple, easy equation to stick into the algorithm to generate the equations. It's basically fixed. But we don't know what the other terms are that go into the x net n. We don't know until all the model is built what are the total flows other than gold purchases. Like, basically we're saying gold purchases cancel all these out. We don't know what those are. So that's how you would be forced to do it if you're doing by hand, if your solver can handle it. And if the solver can handle it, I would have had to force it, find a way so that I could define the gold purchases to do this cancellation, even though we don't know until the model's built what these terms are. But luckily the solver found the solution, and so we didn't have to worry. We could go with the nice short solution. But this is just showing you that using the GUI, that this is how we find the solution to all those equations. We're not doing it's not symbolic. We aren't actually going in doing a linear algebra and matrix inversion or anything like that. We're doing a search technique, which, based on it's a standard mathematical technique used in fixed point theorems, but it's not cannot guarantee. If I didn't have that trick, we would not have found the solution, even though obviously a solution does exist. But over time, as we run into problems, we might have to add more features to the solver to allow it to deal with complicated situations like this, where it looks like it's not convergent, even though we know there's a solution. But basically, my view is we cross that bridge when we come to it. We can start searching in other libraries, but at this point, the overhead of bringing another library is a lot more complicated than just using this fixed point theorem with tweaks to find a solution. Anyway, so that's basically it. I don't have a technical description of the solver. I could publish it eventually, but it's nothing earth-shattering. But there's no guarantee it's going to work. But this is a nonlinear system. There's never going to be a guarantee that you're going to find something that works. Anyways, unless you're in a very precise class of nonlinearities. But since the equations are to a certain extent arbitrary, we're never going to have a guarantee that you're going to converge to the solution. Anyways, that's it for now.